January 31st, 1945, Clark Air Base, Luzon, Philippines. Major Frank T. McCoy's hands shook a little as he took pictures of the plane in front of him, a full Mitsubishi G4M Betty bomber with tail number 76312. This cannot be their normal design. No Air Force would ever build bombers like this. The body shined under the hot sun. Its long, round shape looked like a big metal cigar on the runway. It was about 20 meters long and stood on 3 landing wheels. The wings stretched 25 meters from one end to the other and showed no damage. The 2 engines each had 14 cylinders and made 1,500 horsepower. They looked perfect. This was not a broken plane taken from a crash. It was a complete working bomber left behind by its crew when Americans moved forward. But what really caught McCoy's eyes, what would change, how Americans understood Japanese aircraft, was what he found inside the wings through the small inspection doors. The fuel tanks had no protection at all. No rubber that could seal itself. No armor, no system to stop fires. Nothing, just thin aluminum, maybe 2 millimeters thick, keeping thousands of liters of airplane fuel away from enemy bullets. Major McCoy, who led the Technical Air Intelligence Unit in the Southwest Pacific, had looked at many crashed Japanese planes across the Pacific, but nothing prepared him for this one. This bomber, left whole during the American capture of Clark Field, showed a design idea so strange to Western minds that it took months for experts to understand it. The math from this discovery changed how Americans made planes and planned air battles for the rest of the war. Every belief American pilots had about how strong the enemy was, how much risk Japanese builders would take for speed, and how much they cared about saving their crews was crushed by what they found in this one perfect bomber. The road to this moment had started 4 years earlier, on December 8, 1941. That morning, while smoke still rose from Pearl Harbor, 82. G4M bombers and 26 G3M bombers took off from bases on Formosa. Their target was Clark Field, the main American air base in the Philippines. The attack caught everyone by surprise. At 12:35 in the afternoon, the Japanese flew in at 2,000 feet higher than the range of American anti-aircraft guns. 27 bombers from the first wave dropped 636 bombs across Clark Field's runways and buildings. Moments later, Zero fighters came in low, almost touching the trees, and used their guns to destroy every plane that was still on the ground. Out of 17 B-17 flying fortresses, 12 were blown apart. Almost every P-40 Warhawk fighter was left burning. In just 45 minutes, American air power in the Philippines was nearly wiped out. Lieutenant James Harrington, one of the few American pilots who lived, watched from a bomb shelter as the Japanese planes flew away. He later wrote in his report, "What amazed me was how they came in perfect formation, high up, where we could not reach them. Then, their fighters dropped low and tore us apart. We could not get even one plane in the air. But the Betty bombers left without a scratch. The few American fighters that did get off the ground arrived too late and saw only an empty sky. The Japanese showed how far their bombers could fly, hitting from bases 460 miles away, something no American bomber could do at that time. The Betty's first year in battle turned out to be terribly powerful. On December 10, 1941, only 2 days after the Clark Field attack, 26 G4M bombers joined older G3M Nell bombers to attack Force Z, a British naval group built around the battleship HMS Prince of Wales and the battlecruiser HMS Repulse. The attack began about 12:20 in the afternoon. Japanese bombers came in planned waves, making torpedo attacks with amazing skill that shocked British officers. The Betty bombers carried Type 91 air torpedoes, each weighing 840 kilograms with a 205-kilogram warhead. The torpedoes were made to work well in shallow water, so they could hit ships close to shore. The Japanese pilots aimed their torpedoes carefully at the two big British ships and hit them with deadly accuracy. The Prince of Wales, a huge battleship weighing 43,000 tons and one of the newest in Naders. The British Navy was hit by at least 6 torpedoes and several bombs. The blasts tore open giant holes below the waterline, flooding the ship so fast that the crew could not stop it, and the ship started to tilt badly. The Repulse, an older battle cruiser first built in World War I, but rebuilt in the 1930s, was hit by at least 4 torpedoes while trying to dodge the planes. The ship's guns shot down a few Japanese aircraft, but they could not stop the next wave of torpedo runs. The damage was too much. Both of the big ships flipped over and sank within just a few hours. The Prince of Wales sank around 1320, and the Repulse went down about 1333. A total of 841 British sailors were killed, and the rest were saved by smaller escort ships. The whole fight lasted less than 2 hours from start to finish. For the first time ever in naval history, large warships defending themselves were sunk only by airplanes while out at sea. The G4M Betty bomber had done what experts once thought was impossible. British sea power in Asian waters was broken in just 90 minutes. Through early 1942, across the Pacific, American and Allied pilots kept running into Betty bombers in every major battle. These planes seemed untouchable, flying so far and so fast they hit targets that should have been out of reach. They bombed Darwin, Australia, from bases 1,500 miles away, farther than any Allied bomber could go. They attacked Port Moresby by flying over New Guinea's high mountains, keeping pressure on Allied forces all across the Southwest Pacific. They struck Guadalcanal from Rabaul, more than 600 miles away, spreading Japanese air power over huge stretches of ocean. The Betty's long range gave Japan great freedom to plan and move its forces. While Allied leaders struggled to find a way to stop them, American fighters at front bases did not have enough range to reach the Betty bombers flying from faraway bases. Allied airfields kept getting hit by Japanese bombers that were too far away to strike back at. This difference in bomber range meant the Japanese could attack whenever they wanted, while the Allies struggled to fight back. This edge stayed strong through the first 6 months of the war. Betty bombers joined almost every Japanese attack across the Pacific and Southeast Asia. They hit targets in the Philippines, Malaya, the Dutch East Indies, New Guinea, and the Solomon Islands. They also helped naval missions and flew scouting trips farther than any Allied plane could reach. The Betty soon became a sign of Japan's long reach and air power, but this success only lasted because there were few Allied fighters. When Betty bombers flew high above gunfire, when no fighters could meet them, and when they could drop bombs and fly away safely, they were deadly. These were the kinds of missions they flew in early 1942, when Allied planes were few and scattered. But by mid-1942, things started to change. America's air power grew as older Wildcats were replaced by newer, faster Hellcats, and Corsairs. Pilot training improved, and fighting plans got smarter. Soon, Betty crews started to suffer heavy losses. The big turning point came on August 8, 1942. 23 G4M bombers from the 4th Air Group left Rabaul to bomb American troops at Guadalcanal. American fighters met them over Savo Island. In the fight that followed, 18 of the 23 Betty bombers were shot down. Around 120 Japanese airmen were killed in the worst. Petty loss of the war. Fighter pilots. All said the same thing. The Betty burst into flames with just a few hits. 2 or 3 bullets hitting the body or wings could blow it apart. The plane quickly earned dark nicknames among American crews: Flying Cigar, One Shot, Lighter, and Flying Zippo, all showing how easily the Betty turned into a ball of fire. By October 1942, when Lieutenant Commander John Thomas Blackburn arrived at Guadalcanal, leading VF-17 flying F-4U Corsairs, the Betty's fearsome reputation had completely changed. The first time we caught a Betty formation. We could not believe how easily they went down. Blackburn later said, hit them anywhere along the body or wings and they would explode. We hunted them actively, knowing they were some of the easiest targets in the Pacific sky. But the full reason why the Betty was so fragile, the engineering choices that made these huge losses unavoidable, would only be clear when Americans started capturing whole planes to study. The first big breakthrough came in November 1942, when Australian forces took over Japanese airfields at Buna in Papua New Guinea. Among the abandoned planes, technical air intelligence teams found Betty bombers with different amounts of damage. Early checks confirmed what pilots had said. The fuel tanks had no protection at all. Allied aeronautical engineers from the Technical Air Intelligence Unit in the Southwest Pacific did the first detailed study. The wing panels showed fuel cells with nothing to protect them, thin aluminum. No rubber sealant, no coating, no fire-stopping systems. Multiple Bettys at Buna had the same design. This was not damage from fighting or field changes. This was how Japan built them. The results were shocking. By 1942, all American bombers had self-sealing fuel tanks. The B-17 Flying Fortress had them from the B-17C model. The B-24 Liberator had them from the XB-24B prototype. Even fighters like the P-38 and P-47 had protected fuel tanks. Self-sealing tanks used layers of rubber that swelled when hit by bullets or shell fragments, sealing the hole and stopping fuel leaks and fire. This added a lot of weight but kept crews alive. American military thinking said this weight was essential and could not be removed. Yet Japan's main land bomber, built in thousands across the Pacific, had fuel tanks with zero protection. The weight saved by leaving out self-sealing tanks. Armor and fire systems was clear. But the price in lost crew lives became very obvious as loss numbers grew with every battle. The Betty captured at Clark Field in January 1945 gave the most complete look at its design. Major McCoy and his team spent 3 weeks taking it apart and recording every system. Their secret report was shared with all Allied air forces and gave detailed specs showing both the Betty's amazing strengths and deadly weaknesses. The G4M Model 1 specs showed a plane built fully for range and speed. It weighed only 741 kilograms empty, very light for a bomber its size. Maximum takeoff weight was 9,500 kg, and it carried 4,580 liters of fuel in 8 unprotected tanks, 4 in each wing in the center, where they were most exposed to enemy fire. Top speed was 428 km/h, about 265 km/h. Maximum range, 340 kilometers, over 3,700 miles. Service ceiling, 8,500 meters. Crew of 7 included: pilot, co-pilot, navigator, bombardier, radio operator, and 2 gunners. The fuel design was very revealing. The 8 tanks were in 4 pairs along the wing where it joined the body. This gave maximum fuel because it used the thickest part of the wing, but it put the tanks right in the path of enemy guns. Any side or bottom attack would hit the fuel. Aluminum gave no protection, without self-sealing rubber, even small. Holes leaked fuel constantly. American engineers figured leaving out armor fire systems and self-sealing tanks saved over 500 km plane. This extra weight went straight into more fuel and longer range. But the cost in vulnerability was clear. Combat reports showed Betty's hit in the wing almost always exploded. The unprotected tanks were a critical weak spot, one system whose destruction meant losing the whole plane. These numbers showed the design choices from September 1937, when the Japanese Navy set rules that shaped the G4M's life. Top speed 398, kph cruising altitude 300 meters range, 40 through 722 km empty, or 3,700 kilometers with 800 kLOD. These requirements came from Japan's naval strategy. In the late 1930s, Japan's empire covered huge distances across the Pacific. Naval bases were separated by thousands of kilometers. The Navy needed bombers that could hit targets far beyond the reach of carrier planes. Bombers had to fly from land bases to support naval operations across the whole theater. Existing Japanese bombers did not meet those needs. The G3M Nell in service then had a maximum range of about 3,000 kilometers. Early American bombers, like the B-17, had even less range in their first versions. No bomber anywhere in 1937 could strike the distances Japanese planners wanted. The Navy's requirements were not random. They were based on real distances from Formosa to the Philippines, 460 miles, from Rabaul to Guadalcanal, 600 miles, from Japan to targets across the Pacific, thousands of miles. A bomber that met these rules would give Japan a reach no other nation had, but the requirements also relied on wrong assumptions. Japanese planners thought surprise and initiative would protect long-range bombers. They thought enemy fighter opposition would be limited by range and numbers. They thought the war would be decided quickly before enemy industry could build overwhelming forces. All those assumptions proved false. The engineer asked to meet the impossible was Kiro Honjo. He led Mitsubishi's design team after Joji Hattori. Honjo had studied bomber design at Junkers in Germany in the early 1930s and learned European engineering and production methods. He understood that meeting the Navy's needs would require compromises. Western air forces would never accept. Honjo put together a team of engineers at Mitsubishi's Nagoya plant to solve the design challenges. The team analyzed every part of bomber design and ran careful calculations. The engineers carefully calculated weight for every part and system. They looked at bombers from many countries to see where weight could be cut without weakening the plane. They tried new building methods and materials to save weight. The math was simple but harsh. To get the range the Navy wanted, the plane needed a huge fuel load. Each liter of fuel weighed about 0.8 kg with 780 liters. That meant about 3,800 kg of fuel. To reach the required speed, with all that fuel, the plane had to be as light as possible. Every extra kilogram in empty weight lowered range or bomb load. Fuel was heavy. Protection was heavy. Armor, too. Protect crew and vital parts weighed hundreds of kilograms. Self-sealing fuel tanks added lots of weight from rubber and extra structure. Firefighting systems added weight. Extra safety systems added weight. Altogether, proper protection would make the plane too heavy to perform. Honjo made a choice that defined the G4M for its whole service. Protection would be left out for performance. Fuel tanks were simple, aluminum, no self-sealing rubber, no armor around fuel, no fire suppression beyond. Basic extinguishers, no extra safety. Every kilogram saved went into fuel range and meeting Navy speed and distance rules. The decision was serious. Honjo knew the risks. His team calculated that unprotected fuel tanks could be deadly in combat. They knew damage to the wings could destroy the plane, but there was no other way to meet the Navy's rules with the technology of the time. The choice was clear: make a plane that met performance with known risks, or a plane that was safer but could not reach the goals. The Navy wanted performance. Honjo gave them performance. The first G4M prototype flew on October 23, 1939. The plane met every performance goal the Navy wanted. Speed was higher than expected. Range went farther than predicted. Bomb load met mission needs. The bomber went into production as the Navy Type 1 attack bomber with Mitsubishi, building them in Nagoya. The first production planes, called G4M Model 1, started reaching units in April 1941. By December 1941, about 180 G4Ms were in service with the Japanese Navy. These planes became the main part of Japan's land-based air power across the Pacific. The Betty's first fights at Clark Field and against Force Z showed that Honjo's design choices worked well. In early 1942, when enemy resistance was low, when surprise was possible, and when they flew beyond fighter range, the Betty was deadly. Its long range let it hit targets, thought safe. Its speed let it get into target areas, fast. Its bombs caused real damage. But these benefits depended on having very few enemy fighters. As soon as American fighter numbers grew, when interception became normal, and long fights happened, every design choice that favored range over protection became deadly for crews. The Guadalcanal campaign showed the big flaw in the Betty's design. From August to October 1942, over 100 G4M bombers were lost. Along with their crews in a long period of heavy losses, Japanese forces could not replace them. One mission on August 8 alone lost 18 of 23 planes, with about 120 airmen killed. The same pattern kept happening. Betty groups left. Rabaul flew 600 miles to Guadalcanal, fought American fighters, and were destroyed. August 9th brought more losses. August 10, even more. By the end of August, the 4th Air Group was no longer an effective fighting unit. September gave no break. Bettys kept hitting American positions at Guadalcanal, and American fighters kept destroying them in huge numbers. The math was unforgiving Japanese. Forces had to hit American positions to fight for control of the island. Betty bombers were the only planes that could deliver real damage from Rabaul, but every mission caused losses that could not be replaced. In October, the pattern continued. American fighter numbers grew as more squadrons reached Henderson Field. Pilot skill improved with combat experience. Tactics changed to exploit Betty weaknesses even better. Japanese losses grew even as fewer bombers were available. By November, when the Guadalcanal campaign ended with Japanese withdrawal, over 100 Bettys were lost. About 700 crew members died. The loss rate could not be sustained. Japan's best land-based bomber was made useless by its own weaknesses. It went from a feared weapon to what American pilots called easy meat. Japanese planners expected some losses. All battles have casualties, but Betty losses were far higher than expected. The unprotected fuel tanks that allowed 6 Zuri-Ruderton range also meant any hit to wings or body could be deadly. There was no middle ground, no damaged plane making it home safely. Bettys either came back untouched or burned completely. By mid-1943, Japanese engineers saw that changes were needed. Starting with the 663rd plane, made in March 1943, 30mm rubber sheets were added under the wings where the fuel tanks sat. These were not real self-sealing tanks. They were a compromise, giving some protection while adding very little weight. Top. Speed dropped 9 km/h. Maximum range went down 315, but crew survival did not improve much. The rubber sheets could slow fuel leaks from small bullets, but could not stop fires from bigger rounds or cannon shells. They could not prevent explosions. If tracers ignited fuel vapor, the main weakness stayed the same. Japanese designers tried fuller protection with the G4M Model 3, introduced in October 1944. This version of the Betty had real self-sealing fuel tanks, but fuel capacity was reduced to 4,490 liters. To make room for the leak-blocking material, the change cut maximum range to 3,640 km, losing over 2,000 km, compared to the original G4M model. 1. About 60. G4M Model 3 planes were built by the end of the war. The change came too late and in too few numbers to change the Betty's combat record. By late 1944, American air power was so strong that no amount of fuel tank protection could let Bettys operate effectively. The war's outcome was already decided. The Betty's weakness became so well known that Americans used the planes in ways that showed the dangers Japanese crews faced. On April 18, 1943, a Betty bomber carried Admiral Isoroku Yamamoto and became part of the mission that killed him, showing both American intelligence skill and the plane's fatal flaws. American code breakers had intercepted messages showing Yamamoto would fly from Rabaul to Bougainville on April 22, 18. He would be on a G4M bomber with fighter escort. 18 P-38 Lightnings from the 339th Fighter Squadron were assigned to intercept. Only 16 flew after one plane blew a tire at takeoff and another had drop tank problems. The mission needed perfect precision. The P-38s had to fly over 400 miles at wave-top height to avoid radar, cross the open ocean with no landmarks, and reach the intercept point at exactly the right time. Any navigation mistake or timing error would cause failure. The P-38s left Guadalcanal at 07:25 hours. They flew just 50 feet above the ocean, over 400 miles, and kept radio silent. Navigation was by dead reckoning and careful timing. The formation reached the intercept point with legendary precision at 09:34 hours exactly. On schedule 1 minute early, the P-38 spotted Yamamoto's formation. Two Betty bombers flew low with 6 Zero fighters. As escort, Captain Thomas Lanphier and First Lieutenant Rex Barber broke from the main group to attack the bombers, while the other P-38s kept the Zero fighters away. Barber went after the lead, Betty bomber carrying Admiral Yamamoto. The plane was hit in the wing, where the unprotected fuel tanks were, and it exploded in flames, crashing into the jungle. Yamamoto's body was recovered, but he died the following day from injuries sustained in the crash. The second Betty bomber also went down, and everyone on board died. The operation showed many aspects of Allied superiority. American signals, intelligence had intercepted and decoded Japanese messages. American planners calculated the intercept timing to the minute over 400 miles of ocean, and American fighters carried out the mission perfectly, despite extreme navigation challenges. The Betty bomber's weaknesses made any interception deadly. There was no chance for Yamamoto's plane to survive once attacked. The unprotected fuel tanks made any damage catastrophic. The Betty's vulnerability reached its most dramatic moment on March 21, 1945. 18 G4M bombers took off from Kanoya Air Base, each carrying an MXY-7 Oka rocket plane under its fuselage. The Oka was a small piloted rocket with a 200-kilo warhead designed for kamikaze attacks on American ships. The mission required the Bettys to fly within 20 km of their targets before releasing the Oka. The pilot would ignite the rocket motor and dive at speeds over 650 km per hour toward the ships. The 200-kilo warhead could destroy any ship it hit, but the mission depended entirely on the Betty bombers surviving long enough to reach release range. The formation left Kanoya at about 14:30 hours. 18 G-4M bombers flew tightly with fighter escort toward American naval forces off Okinawa. Each plane carried an Oka under its fuselage, adding heavy weight and drag, which reduced speed and made maneuvering much harder. The bombers were even more exposed than usual. They could not dodge or move properly while carrying the Oka rockets. American radar spotted the group at about 100 miles. F-6F Hellcat fighters from the USS Hornet were scrambled to intercept. The Hellcats reached the Japanese formation long before the bombers could release the Oka weapons. In the fight that followed, American fighters destroyed the entire formation. The Betty bombers, already weak under normal conditions, were completely helpless with the Oka rockets. The extra weight stopped them from dodging. The rockets under the fuselage created drag and slowed them. The unprotected fuel tanks meant any hit was deadly. One by one, the bombers blew up and fell into the ocean. Not a single Betty reached release range. Not a single Oka was launched against American ships. 137 bomber crew members and 15 Oka pilots died in the attack. The mission showed the ultimate flaw of the Betty A plane built to hit faraway targets could not survive long enough to drop its weapons. Even the long range that made the mission seem possible meant nothing because the planes exploded before reaching the release point. The last mission flown by Betty bombers was on August 19, 1945, just 4 days after Emperor Hirohito announced Japan's surrender. 2 white-painted G-4M bombers with green crosses left Sugi Airfield carrying Japanese officials to talk surrender. With Allied forces, the planes had call signs Baton 1 and Baton 2. They flew to Iwo Jima, where the Japanese delegation switched to an American C-54 to go to Manila. The symbolism was clear and intentional. The white paint and green crosses showed peace turning the bombers from weapons into diplomatic vehicles. The call signs Baton 1 Hantin, Aonda, and Baton 2 referred to the place where American forces surrendered to Japan in April 1942, one of America's worst military defeats. 3 years later, planes with those call signs carried Japan's surrender. Lieutenant Den Sudo piloted one of the surrender planes, a G-4M Model 1 transport, converted from the bomber design. The transport versions kept the Betty's unique cylindrical body and wing shape, but carried people and cargo instead of weapons. The crew wore dress uniforms instead of flight suits. The planes had no weapons, no ammo, no military gear except what was needed to fly. The flight from Atsugi to Iwo Jima was about 1,000 kilometers well within the Betty's range, even as a transport American fighters escorted the white Bettys with green crosses the whole way, making sure they stayed on course. The escort was both protective and supervisory, keeping the planes safe and, on the planned route, the white Bettys became the final image of the aircraft that started the Pacific War at Clark Field in December 1941. The circle was complete. The bomber that destroyed American air power in the Philippines at the war's start now carried Japan's surrender officials in the final days. The plane that had shown Japanese air power and reach now symbolized Japan's defeat and submission. The Betty's production numbers show both its importance to Japanese operations and the high cost of its design philosophy. Total production was about 2,414 planes, across all versions, though some sources say 2,435 counting prototypes and subtypes. Differences in totals come from counting prototypes, subtypes, and transport versions separately. The G-4M Model 1 had about 172 planes built from 1941 to early 1943. This version had the original unprotected fuel tanks with four 780 liters capacity. Top speed was 428 km per hour. Maximum range of 6,034 km. Patter made it the longest-range bomber in the world, but the lack of any protection made it extremely vulnerable once American fighters got stronger. The G4M Model 2 had more fuel and slightly higher speed and made up about 142 examples were built from 1943 to 1945. This version increased fuel capacity to 6,490 liters, giving even longer range. Top speed rose slightly to 437 km per hour, but Model 2 still had the same basic weakness of unprotected fuel tanks. The changes made performance better but did nothing for survivability. The G4M Model 3, called Model 34, was the only version with real self-sealing fuel tanks. Production started in October 1944, but only 60 to 91 planes were finished by war's end. Depending on the source, the self-sealing tanks cut fuel capacity to 490 liters to fit the leak-blocking material. Maximum range dropped to 3,640 km, a loss of over 2,000 km compared to Model 1. The change came too late, and too few planes were made to change combat results. The G6M transport variant converted from bomber airframes added another 30 planes. These transport versions carried people and cargo instead of weapons and were used for liaison and communication duties. The G6M Model 1, used for one of the surrender flights in August 1945, was this type. Production went on through August 1945, with the last planes finished just days before Japan surrendered. Mitsubishi factories built Betty bombers at peak rates of about 100 planes per month. In 1943, production dropped in 1944 and 1945 as Allied bombing hit Japanese industry and resources were shifted to fighter planes for homeland defense. These production numbers made the Betty one of Japan's most numerous bombers, only surpassed by some fighter types. Over 4 years, Mitsubishi delivered about 400 planes to Japanese Navy units across the Pacific. The bombers served in every major campaign, joined every important naval battle, and hit targets thousands of kilometers away. But production numbers tell only part of the story. Losses tell the rest. Few Betty bombers survived to the end of the war. Most were destroyed in combat, burned by the fires that unprotected fuel tanks made inevitable. By August 1945, when Japan surrendered, only a small number of operational Betty bombers still in service were very few. The planes that had numbered in the hundreds in 1942 had been cut down to only dozens, by losses that production could never replace. Casualty numbers for Betty crews were just as severe, though exact figures are hard to confirm from records. What is clear is that thousands of Japanese aircrew died flying Betty bombers. Their deaths were almost guaranteed by the aircraft's main weaknesses. The unprotected fuel tanks meant survival depended entirely on avoiding any combat damage. Once hit, a Betty rarely survived. Once on fire, it never survived. Crews knew the odds and flew. Anyway, because military discipline and cultural values demanded they accept the risks, surviving Betty crews all agreed. The unprotected fuel tanks made survival pure luck. No skill, no tactical idea, no bravery could make up for the built-in weakness. In every G4M, former flight petty officer Masawato, who flew 28 combat missions before moving to training, gave the clearest summary. The Betty was an amazing plane that asked us to die for its long range. We flew it because we were told to. We died in it because that was what it was designed to do. Comparing Allied bombers shows the huge difference in design thinking. The B-17 Flying Fortress had armor protecting the pilot and co-pilot seats with steel plates 0.3 to 0.31 inches thick. Armored. Bulkheads protected crew positions throughout the fuselage. The Bombardier had armored glass. Waist gunners had shields. Self-sealing fuel tanks were standard from the B-17C model onward. The B-25 Mitchell, introduced in 1941, had similar protection. Pilot and co-pilot seats had armor. Fuel tanks had self-sealing material from the start. The B-25's empty weight was about 100 kilo, reflecting the heavy cost of protection, about 2,000 kilos more than the Betty. Even though similar in size and role, the weight cost for Allied protection systems was very high, but seen as necessary. American studies during the war proved that protecting crews worked body armor lowered chest wound deaths from 36% to 8%, cutting deaths by more than 75%. Self-sealing fuel tanks reduced fire deaths by similar amounts. Aircraft with protected fuel systems survived 3 to 4 times more often than unprotected planes when hit in combat. Protected crew positions shielded people from shell fragments and small arms fire. Armored glass kept pilots safe from head-on attacks. Bulkheads divided the fuselage, so damage or fire in one section didn't spread. The full approach to crew protection reflected American thinking. The trained crews were more valuable than planes, which could be replaced. The weight added for this protection often exceeded 1,000 pounds in American bombers, but the U.S. could handle this without hurting production factories built over 12,000 B-17 bombers and nearly 10,000 B-24 Liberators during the war. This capacity let Americans field large numbers of protected bombers without losing capability. Japanese doctrine thought differently. The Betty's design showed they believed range and firepower were more important than crew survival. They assumed surprise and initiative would protect their crews. They assumed enemy resistance would be limited. They assumed the war would be quick. All these ideas were wrong. By mid-1942, American fighter strength had grown, so Betty interception was normal. By late 1942, American pilots knew how to exploit every Betty weakness. By 1943, Betty missions became almost suicide missions. By 1944, Betty bombers could barely fly in daylight. Against American forces, the story of the Betty's war was written in fire and loss. Every advantage that made the Betty bomber so dangerous in early 1942 became useless once real combat lasted over time. Range didn't matter when the planes exploded. Before reaching their targets, speed didn't matter when American fighters could intercept from far away. Payload didn't matter when entire formations were destroyed before dropping weapons. Examining tail number 763-12 at Clark Field in January 1945 showed the full story. The unprotected fuel tanks that shocked Major McCoy were not a mistake, not a temporary fix, not poor design. They were a deliberate choice by engineers who thought range was more important than survival. Japanese designers had built exactly what their instructions demanded. An aircraft with amazing range and speed, very light, made to meet the mission goals they were given. The fuel tanks were unprotected because adding protection would have stopped the plane from meeting performance requirements. The decision made sense for 1937 technology and the 1937 ideas about future warfare. But those ideas failed when the planes faced long battles against an enemy with endless industrial power and better technology. The Betty bomber became a symbol of Japan, accepting huge losses for tactical advantage. It showed a military culture that valued mission success over crew safety. When American engineers studied the intact Betty at Clark Field, they were not just looking at an enemy plane. They were seeing the real results of choices made years earlier. choices that put capability above survival, choices that cost thousands of Japanese aircrew their lives. The unprotected fuel tanks were not accidents, they were decisions. The Betty bombers served from the first day of the Pacific War to the last. It sank capital ships and destroyed air bases. It flew farther than any other bomber. But its ultimate story is written in the losses that were far higher than anyone expected. The aircraft that started the war by smashing American air power at Clark Field ended the war carrying Japan's surrender delegation in white-painted planes with green crosses. The crew of tail number 76312. The crew of tail number 76312 had abandoned their aircraft during the American advance on Clark Field. They survived by walking away from a plane whose design made surviving combat almost impossible. Most Betty crews were not so lucky. They flew missions knowing the danger. They climbed into unprotected bombers, crossed vast Pacific distances, and died in overwhelming numbers, consumed by fires the aircraft's design made inevitable. The Betty bombers' story is ultimately about the cost of capability without protection. It shows that performance alone cannot guarantee success when that performance comes at the cost of crew survival. The extraordinary 6 kilometers range meant nothing when planes couldn't survive the last 100 kilometers to their target. The impressive 428 km/h speed gave no advantage when American fighters could intercept from distant bases with radar warning. The 1-ton payload capacity became irrelevant when formations were destroyed before dropping weapons. Most importantly, the Betty shows that military technology divorced from realistic combat assessment produces weapons that kill their own crews as efficiently as they hit the enemy. The assumptions behind the Betty's design, expectations of limited opposition, and short wars proved catastrophically wrong within months of the Pacific War's start. By the time these assumptions were shown false, thousands of Betty bombers were already in service or production, and Japanese industry could not replace them with better protected designs. Japanese designers understood the risks when they made their choices in 1937 and 1938. They calculated weight penalties. They knew the vulnerabilities. They accepted the trade-offs, believing the performance advantages would be decisive. They were wrong, and thousands of men paid with their lives. The Betty's legacy goes beyond aviation history into core questions about aircraft design, philosophy, military ethics, acceptable risk, and the value of human life in warfare. American designers answered. By prioritizing protection, even at the cost of performance, Japanese designers answered differently. It stands as evidence of what happens when capability is valued above survivability, when range is bought with crew lives, when performance requirements override protection considerations. The thousands of burning Betty bombers across the Pacific sky marked the consequences of that philosophical choice, revealing the fundamental difference in how nations approached warfare. In the Pacific, American forces designed aircraft to bring crews home. Japanese forces designed aircraft to reach targets regardless of cost. In the end, the nation that valued crew survival built an air force capable of sustaining operations indefinitely. The nation that accepted catastrophic casualties for performance gains built an air force that destroyed itself through attrition. The examination of tail number 763-12 at Clark Field provided final proof of what Allied forces had suspected for years. The Betty bomber was not poorly designed. It was brilliantly designed to achieve very specific goals. Those goals simply did not include bringing Japanese crews home alive. And in that single fact lies the entire story of why Japan lost the Pacific.